Um, Let me show you the tutorial sheet if you haven't seen it before. So if you go to week 6, this is the tutorial sheet. There are 10 questions. I will try to do as many of them as possible. Okay, I will start with question 10 and work backwards, because question 10 is the most recent stuff I have done. All right, so I will start with question 10 and work backwards. Okay, right. And as usual, if you have any questions, guys, please please feel free to use the chat room. Right. So let's start with question 10. I don't know whether you can. Let me change the camera. So I don't know if you can see this. So maybe not very well. I don't know. Maybe you have problems seeing this. I don't know. Let me try to. Excuse me. I guess it's really difficult to see it. Okay. Maybe it's slightly better now. Can you see it now? Or let me adjust this. Oh, sorry. If you can't see it, try to use the online the PDF file in the course website, which you should be able to see on your laptop or whatever you have. All right, so I'm sorry for this, but I'm having difficulties focusing this. Right. All right, so I will start with question 10. Question 10 is, I'm sure you can read it from your laptop, what question 10 is about, right? So you have a random sample from a binomial distribution with parameters m and p. So let me write this down. Hopefully you can see this better. Question 10. Oh man. Excuse me. Question 10. All right. So you have random sample x1 to xn, which are IID from a binomial distribution with parameters m and p. And the question is that you are given an estimator p hat, which is equal to x bar plus 1 divided by n plus 2, right? And the question is to find the bias and the variance of this estimator as an estimator of p, right? So the first thing I'm going to do is I'm going to find the bias of p hat, right? Which by definition is the expectation minus the parameter that you're trying to estimate, which is the expectation of x bar plus 1 divided by n plus 2 minus p, right? Okay, guys. So I think the sun is directly coming into my eyes, so it's not a good thing, right? So if you take the expectation inside, you can write this as 1 over like this. Yeah. Please, if you have any questions, please feel free to use the chat room, guys. Okay. Now, XBAR, I'm sure all of you know, is this. Yeah. Okay. And now, if you take the expectation inside the open brackets here, you will get 1 over right. Now, I'm sure all of you know that the expected value of a binomial variable is m times p. So this becomes m times p, right, plus, yeah. Okay, now mp is a constant with respect to I. So sum of a constant is constant n times the constant. So this will be, n times the constant, which is mp, right? Right. Now, if you simplify this, this is what you will get. You get mp plus 1 divided by n plus 2 minus p. All right, so this is the bias of the estimator that we are trying to. This is the estimator, and what we just worked out is the bias of it, right? Okay, guys. Are you okay so far? Any questions so far? Hello, guys. Talk to me. No. Okay. Thank you. All right. Now, as n goes to infinity, this guy here goes to 0. So what you have is this goes to minus p as n approaches infinity, right? So remember the definition of asymptotic unbiasedness. An estimator is said to be asymptotically unbiased if the bias approaches 0 as n tends to infinity, which is not the case here. So what you can say is that p hat is not asymptotically unbiased, right, for p. Right, it's not asymptotically unbiased estimator for p, because if it is asymptotically unbiased, then it must approach 0. The bias must approach 0 as n goes to infinity, which is not the case here. Right? Are you okay with this first part of question 10, guys? Yeah. Yeah. Okay. Thank you. All right. Let me now do the second part of question 10. The second part is to find the variance of this, right? So I want to show you how to find the variance of the estimator x bar. Okay. Now this you can write as the variance of you can write it like this. Yeah. I'm sorry that the sun is coming straight at my eyes. So I don't know why it's not. Excuse me. Hope you can see this. Hope you can see what I'm writing. Okay, now this is a constant, right? So remember, the variance of a variable, of a random variable plus a constant is the same as the variance of the random variable, right? So this you can write as the variance of x bar plus n plus 2, right? Because of what I just said, that the variance of a random variable plus a constant is the same as the variance of the random variable. Now this n plus 2 here is a constant. So when you take it outside, it becomes this, yeah? Okay, guys. Now this, right, variance of okay. Are you following me? Now, taking the n outside of the brackets, you will have this, yeah? Now, I'm sure all of you know that the variance of a binomial variable is mp times 1 minus p. So this is okay. Now, once again, this is a constant with respect to I. So sum of a constant is n times the constant. So you get what you have is n times the constant. Right, so this becomes equal to mp1 minus p divided by n plus 2 squared times n. Okay. All right, and as n approaches infinity, this approaches 0. Okay. All right, so this completes question 10. Are you okay with this, guys? So I just finished the solution for question number 10. Is that fine with you? Any questions you have? Are you confident? Okay, good. All right, so let me go to the next question, which is, so I'm done with number 10. All right, number 9, hopefully you can read this, or you can read it off your laptop. You have a random sample from a uniform 0 theta, right? And you have this estimator for theta, which is theta hat equal to k times x bar, right? You have okay, and the question is whether this, find the value for k such that this estimator is unbiased. Okay. All right. So this is question 9. So you have a random sample x1 to xn, which are IID from a uniform distribution on the interval 0 to theta, right? And you have this estimator that is theta hat is equal to k times x bar. And the question is to find k such that this estimator is unbiased for theta. Okay, so what you need to do is to find the bias. All right, so you need to find the bias and show that and see for what value of k the bias is 0. Okay. Okay. Now k is a constant, so you can pull it outside. So this becomes, yeah. Okay, guys. Now, so this becomes k times the expectation of x bar, which is 1 over n times the sum of xi. Yeah. Now, taking the expectation inside the brackets, you have k divided by n. I'm sorry for the quality of the visualizer. It's just not. I hope you can see my writing. Please let me know if you cannot see my writing on the visualizer. Right, please let me know. Right. Okay, now the expectation of xi is the expectation of a uniform variable on the interval 0 to theta. Now, you may know from probability 1 that if you have a variable x that is uniformly distributed on the interval, say, a to b, right, then the expectation of x is equal to a plus b divided by 2. Do you remember this formula, guys, right? This is something you probably did in probability 1, right? So let me put this in a box, okay? All right, now using this formula, you can work out the expectation of xi for a uniform 0 theta, right? So this will become k over n times the sum of theta by 2 minus theta, right? So this will be k over n multiplied by n theta by 2 minus theta, right? Okay. Now the n and the n cancel, so this becomes k theta by 2 minus theta, and this is equal to 0 if and only if k is equal to 2, right? All right, so what I'm saying is that the estimated theta hat with k equal to 2, right, is an unbiased estimator of theta. Okay, do you follow this, guys, so far? Hello, guys. This is clear so far that k is equal to 2, and therefore theta hat equal to 2 times x bar is an unbiased estimator of theta. Any questions so far, guys? Please let me know. Please talk to me. Hello, guys. Are you okay with me so far? Before I do the next part of question. Okay. The second part of the question is to find the variance of theta hat. So I'm going to find the variance of 2 times x bar in the next part of question 9. Right? This is still question 9. I'm going to find the variance of theta hat, which is 2 times x bar. Now, if you pull the 2 outside the brackets, it becomes 4 times the variance of x bar. So this is 4 times the variance of 1 over n times the sum of xi. Now n, if you pull the n outside of the variance sign, it becomes 4 divided by n squared times the variance of the sum of xi. Now you take the variance inside the sum, you get 4 over n squared times the sum of this. Now, once again, you may know from probability 1 that if you have a variable x that is uniformly distributed on the interval from a to b, then the variance of x, right, is equal to b minus a squared divided by 12. Do you remember this, guys? Hello, guys. Do you know this formula or no? This is a formula for the variance of a uniform variable. Yeah. So if you use this formula, guys, this is what you will get: 4 over n squared multiplied by the sum of theta squared divided by 12. Okay. So this is 4 over n squared multiplied by n theta squared divided by 12, right? And this simplifies to the following: theta squared divided by 3n. Okay, and this approaches 0 as n approaches infinity. All right, so the variance, I mean, this is what you will expect, that the variance to approach 0 as the sample size approaches infinity. All right, so this completes question 9. Are you okay with this, guys, or not? Hello, guys, talk to me, please. Everybody okay with question 9? Okay, thank you. All right, so let me now go to the next question. So I'm working from backwards, if you noticed. So next one is question 8, all right? Question 8, you have, I don't know if you can read it. It says you have a random sample from a population with mean 0 and variance sigma squared. And the first part is to find a k such that this estimator for sigma squared is unbiased for sigma squared, right? So let me show you how to do question 8. So this is question 8, guys. So you have this estimator for sigma squared, which is k times and we want to find k such that this estimator is unbiased for sigma squared. So what you need to find is you need to find the bias of the estimator and set that equal to 0, and then from that equation you'll be able to figure out what k is, right? So remember, the bias is defined as the expectation of the estimator minus the parameter that you're trying to estimate, right? Which is okay. Now k is a constant, so you can pull it outside. So this is k times the sum like this, yeah. All right, now I'm gonna use a trick here. I'm gonna do the following trick. You see why I'm doing this in a sec. You see what I have done here? You see, I have subtracted this term here and added the same term, so I haven't changed anything. Now, let me ask you something. If you look at these two terms, what do you see? This minus this is what? Can you recognize it? Hello, guys. This minus this is, it should be something familiar to you. Yes, you're right, Sophie. So this is equal to the variance of xi. Yeah, this minus this is the variance of xi. So what you have is, all right, now you should go back to the question. Let's go back to the question. The question says that the mean of the population is 0 and the variance of the population is sigma squared. So returning to this guy here is equal to sigma squared, and this guy is the mean of the population is equal to 0, right? All right. So what you have is k sigma squared plus 0 minus sigma squared, right? Now sigma squared is a constant, so the sum of a constant is n times the constant. So you have k times n sigma squared minus sigma squared, and this is equal to 0 if k is equal to 1 over n. All right, so in other words, what I have shown is the following, that okay. All right, guys, so that's the first part of question 8. Are you okay with this or no? So the trick I have used is this one here. To go from this line to this line, I have used this trick here. All right. Are you okay, guys, or no? Hello, guys. All right. So that's part 2. Okay, now let's go to the part 2. The second part of question 8 is to find the sampling distribution if assuming that xi are independent normal with mean 0 and variance sigma squared. All right. So let me show you how to do this. So this is still question 8, part 2. Okay. So you have, you have sigma, the estimator is 1 over n times the sum of xi squared, right? This is the estimator that we have. Now we want to find the sampling distribution of this. Now we are told that xi is normal with mean 0 and variance sigma squared. All right. Okay. So I'm replacing xi by this normal variable. Now the next thing I'm going to do is the following. I'm going to All right, you have this. Okay, now let me ask you something. If you divide a normal variable with these parameters by sigma, what would you get? You should divide, I mean, I'm talking about this term here. You should divide a normal variable with sigma. It's basically what I'm asking you is the normal standardization. Remember, to standardize a normal variable, you subtract the mean and divide by the standard deviation. So what you're doing here is precisely that. You're dividing by the standard deviation. So you get this, right? Now the sigma you can pull outside, so this becomes sigma squared by n times the sum of this, right? Are you with me so far? If you have questions, please feel free to use the chat room, guys, please. All right, now, I don't know whether you remember that in the video on chi-square distribution, I know it's some time ago, you should look in the video, you should look at the video on the chi-squared. If you look at this video, which is one of the videos in the course website, right, you will see that one property that I mentioned in that video is that if you square a standard normal variable, what you get is a chi-squared variable with 1 degree of freedom. This is one of the properties I mentioned in this video. Another property that I mentioned in that video is that if you sum two different, in this case, n different chi-squared variable, what you get is also a chi-squared variable, right? But with the degree of freedom being the sum of the degrees of freedom. So you have 1 repeated n times, so the sum is gonna be n. So both these properties follow from the video on chi-squared distribution. So please, if you don't remember the properties I talked about, please have a look at this video one more time. Okay. Are you guys okay with this? Hello. Hello guys, talk to me. So this completes question number 8. Yeah. All right, can I move to the next question, guys? Okay. So this question 7 is this one. So you have a random sample of size 10 from a normal with these parameters. The first part is to find the probability that the sample variance is between 25 and 60. So this is question 7. You have you have 10 random numbers which are IID with normal with parameters 48 and 36. Okay, and we want to find the probability that in part 1 that the sample variance is between 25 and 60. Right. Okay. Now remember, this is the notation I use for the sample variance. I gave you 2 different definitions. One is the biased version, the other one is the unbiased version. And I told you the unbiased version is the better of the two. So I will use that, right? So the unbiased version is where you have 1 divided by n minus 1. N minus 1 is 10 minus 1 here. N is the sample size, which is 10 here, right? Times okay, this is what you get. Right now, 10 minus 1 is 9. Now, what I'm going to do in the next step is I'm going to multiply everything by 9. All right, so this is going to be 9 times 25 less than or equal to okay. All right. All right. In the next step, I'm going to divide everything within the brackets by 36, which is the variance, population variance. I will explain why I'm doing this in a minute. Okay. All right. I don't know whether you recall, I don't know if you remember that the following result, that if you have a random sample x1 to xn, which are IID, right? Then the following result is true. I mentioned this result some time ago, you may recall. Do you remember this, guys, or not? So let me put this in the box so you may remember this. So you should, once again, you should look at the video on the chi-squared distribution. You will see this. This is one of the properties I mentioned in that video, right? That if you have a random sample of size n, right, then this is true. From a normal, then this is true, right? So I'm going to use this result over here. You see what you have here is exactly of this form, where sigma squared is 36, right? All right, so using this result, this one you can simplify to 25 divided by 4. And using this result, this guy will become chi-squared with 9 degrees of freedom. And this one simplifies to 15. All right. You see that? Yeah. Now, you can write this probability as this. Yeah. All right. And if this is simply the CDF of a chi-squared variable with 9 degrees of freedom at 15. And this is the CDF of a at 25 by 4, right? Now this one you can read this if you have the R open in front of you. You can read this of R using the following command. this command pchisq computes the probabilities of a chi-squared variable. So if you say pchisq at 15 with the df stands for degree of freedom equal to 9, this will compute this probability here minus pchisq 25 by 4 df equal to 9. It will compute this probability here. So if you take the difference of these two, you will get the answer to the question that the probability that the sample variance is between 25 and 60, right? Okay, guys. So this is part 1 of question 7. Are you okay with this? Hello, guys. Talk to me, please. Hello. Hello. Thank you. All right. So let me now try to do part 2. So I've done part 1. Part 2 is to find the sample size such that the probability that s squared is greater than 20 is 0.9. Okay. All right. So this is question 7, part 2. So we want the probability. We want the probability that s squared is greater than 20 to be equal to 0.9. Right? Okay, so let's see how we can do this. So this is gonna be the formula for s squared is, as I already mentioned, is this. Okay. Now the next thing I'm gonna do is I'm gonna multiply both the left and the right by n minus 1. So you get the probability like this. Yeah. All right, the next thing I'm going to do is I'm going to divide both sides, the left and the right, by the sample variance, which is 36. You may recall from part 1. So I'm going to divide the left-hand side by 36. And also divide the right-hand side by 36. Okay. All right, now using the results that I mentioned in part 1, which is this. Remember this result here, guys. Right, using this same result, right? The left-hand side must have a chi-square distribution with n minus 1 degree of freedom, right? And the right-hand side, you can simplify to 5 times n minus 1 divided by 9 equal to 0.9. Okay. Are you with me, guys, so far? Hello. Okay. All right. Now, next, I'm gonna write this as 1 minus the probability that the chi-squared variable is less than or equal to is equal to this, right? So the probability that this will become equal to 0.1. Okay. Now you cannot solve this by hand. So to solve this, once again you will need to use R. So in R, you can write the left hand side as follows, as P chi-squared 5 times n minus 1 divided by 9. Okay, and the right hand side is 0.1. Right. Now, if you solve this using R, you will get n is the sample size, to be approximately equal to 15. All right. Okay. All right, guys. So this completes question 7. Are you okay with this? Hello, guys. Talk to me. Yeah. All right. So, and the next question, I don't know if I have time for that, but the next question, so we're done with the last 4. The next question is question 6. Question 6. Maybe I will do the first part of question 6 if that is okay with you guys. The second part is not difficult. So I will just do the first part. Okay. So basically, you have a random sample x1 to xn, which are IID from a Poisson distribution with parameter lambda. The question is to find the sampling distribution of x bar. So you have this estimator lambda hat, which is defined as x bar. And the question is to find the sampling distribution of the mean and the variance of this. So to find the mean, you take the expectation of lambda hat, which is the expectation of x bar, which is the expectation of this, right? Now, if you take the n outside, this will be 1 over n times the sum of the expectation of xi. Now, you may recall from probability 1 that the expectation of Poisson is what? You remember? The expected value of Poisson is lambda, right? The expected. All right, so this is 1 over n times n lambda, which is lambda. All right, so that's the expected value. Now, to find the variance of lambda hat, the procedure is the same. So you find the variance of x bar, and this is the variance of 1 over n times the sum of xi. Yeah. Now, if you take the n outside of the brackets, n becomes equal n squared. Now, once again, you should know from probability 1 that the variance of a Poisson random variable is lambda. Okay, so this is 1 over n squared times n lambda. So this is equal to lambda by n. All right. So that completes the first part. So the expected value is lambda, and the variance is lambda by n. And therefore, if using the Using the central limit theorem, you can approximate by the central limit theorem. You can say that lambda hat is approximately normal with the mean equal to lambda, the variance equal to lambda by n. All right, so this completes part one of question 6. Part 2 is easy. I'm sure you can do it by yourself. But in any case, I will post the full solutions to all the 10 questions on Thursday of this week. So if you go to the course website on Thursday, you will see the typed solutions, the handwritten solution, and the video solutions. So there are three versions of the solutions for all the 10 questions in this tutorial sheet. All right, guys. Are you okay, guys? Any questions you want to ask on stuff I covered today, including the tutorial session? Are you sure? All right. So if you have any questions you want to ask later, please contact me 24/7, okay, by email or Skype or Zoom or phone. All right. My phone number is 0161 273 2941. Thank you, guys. Have a great evening, and I'll talk to you guys soon. Okay, bye.